sure.
Yeah.
I think today is a very hard day because lots of things in life. Oh, sorry. You think I'm start? Okay. Good afternoon. I will try to finish you today. I'll let you go to bed after this class. My name is Danilo Reitano. I don't know if you know me. I come from Sicily, Italy, and I work at Istituto Nazionale di Fisica e Vulcanologia, INGV, National Institute of Geophysics and Volcanology, and we talk about INGV and the relationship between INGV and civil protection, obviously in Italy. So, just to say 2 words about me, not to tell you my life, but also to give you an example how a project Erasmus can be useful for you when you are lucky to participate. And then we talk not only what is INGV, but why INGV exists. Then the relationship between INGV and Civil Protection Department, some details on monitoring networks, and then the use of data. And so at the end, some practical procedures that we use currently in INGV and in our control rooms. So let's start. I'm not a geologist, as you say. I'm an engineer, and I am a technologist inside INGV, and I work in Catania branch. And just to tell you 2 words, not only for me, because when I started in 1997, INGV doesn't exist at the time, but I was involved in National Program for Research. There is point. Oh, sorry. National Program for Research in Antarctica, South Pole. So I was new in geological matters. I was new to see an Institute of Volcanology, and then someone told me, okay, we have a seismic network, we have seismic seismometers and seismic devices. You have to build a transmission system and then put it in the South Pole in Antarctica. So my first question is, okay, what is a seismic network? I don't know, what is a seismic digitizer, for example. I try to understand, but it's not so simple. And that's why this summer school is very useful for you, because you have to share knowledge between you and try to learn more you can. Sharing inside your tables or talking to other people. At the end, in 1998, I went to Antarctica. I spent most of the month there, and we installed the network, the transmission lines, and it worked. So I was very glad. Then, in 1999, INGV was created. We decided to create a department inside the Institute and in Catania branch, and we define a department that is called Control Room, and I worked a lot there. And still now I'm working on data management, where I was very useful this morning to tell you about metadata, data interoperability, and words like this. Okay, So let's start with the first question, but please help me to interact with you, because otherwise we will sleep, everybody. So why INGV? I don't want to, I told you that I'm not a geologist, but I want to start from the reasons, and you know everything about earthquakes, epicenters, their distribution, but not only. You know better than me what is crustal plate boundaries and why earthquakes are here. If you see in the red dot, earthquake epicenters in 10 years all around the world, they are perfectly coincident with the plate boundaries. So we look like the situation in Italy, where plates and zooming in Italy, you can see Alps, Apennines, and also the southern part of Italy, especially in Sicily, where I live.
Sorry, Danilo. I just to say hello, everybody. I'm going back to Italy.
Thank you so much, Fabio.
Goodbye.
Goodbye.
See you soon.
Have a nice trip.
Ciao, ciao. Ciao.
So I think it's clear what are the reasons why this happened. And in particular, in 2011, when we celebrate the 150 years of the unity of Italy, we create a special map using the Italian flag. Green, white, and red, with, sorry for the Italian, low seismic risk and high seismic risk. As you see, it is perfectly what we have seen before. And it is a real distribution of earthquakes. In fact, I have taken this from the INGV website that regards earthquakes, and this is a situation of more or less 2 months, maybe 3, and you can see, oh sorry, and you can see there are lots of earthquakes where, when we saw Apennines, eastern part of Sicily and South Italy, and then something here. Please, let's have a look in particular in my local region. So we consider only the eastern part of Sicily, because I will tell you why it is more active, and so we define the local plate, faults, and also what's happening. The European plate and the African one. Try one to be different, and the result is this. This is 10 years of the situation of 10 years of earthquakes. I don't have doubts to show you Mount Etna, show you the southern part of Sicily, but also Aeolian Island. So there are some hotspots, and we have lots of earthquakes, but also we have some other things. Volcanoes, active volcanoes. In the center, I will introduce Mount Vesuvio. On the left, Mount Etna volcano, and then Stromboli one. Do you know this? Not only the Italian, the activity of this volcano. So that's why INGV is, and we will see that we are in Catania, we are, for example, in Naples, and so on. So something about Mount Etna volcano, that is the largest and tallest volcano in Europe, and it is one of the most active in the world. So it is a very special active laboratory that we have, and we can study lots of its eruption. At the moment there are 4 crateers, and their names are Voragine, Bocca Nuova, Northeast Crater, and Southeast Crater. As you can see, they are not. They were not born in the same years. So in more or less 30 years, the situation of the summit craters completely changes. Try to imagine what we can do with virtual reality to reconstruct this history. It's amazing. And otherwise, we have maps. We have we can see photos, so maybe some video. But we have not the opportunity to collect all the data we have now. I will present another one, Mount Stromboli volcano, 12 square kilometers. It's an island, as you see. It is in a relaxed version, so it's like us at the moment. But be careful, because we know Stromboli is a different behavior. So can we say that it's now still relaxed? It is a photo taken in 2002, part of Sciara del Fuoco. We saw this morning, Vera showed us a part of the volcano collapsed, and it was a submarine tsunami also, and it was a very big problem. So that's why INGV. That's why INGV is here. Here is also in Palermo. Is also in Naples, in Rome, in Bologna, in Milan, and lots of other little departments. We have to monitor earthquakes all over the Italian country, and monitor active volcanoes that are Mount Etna in particular, Aeolian Island, Vesuvio, and the island of Pantelleria, and so on. So, l'Istituto Nazionale di Geofisica e Vulcanologia has, we can say, has 3 different souls. The first is a research institute, so it follows the rules of a research area with scoring, publication, and so on. But just a little bit to be more clear, INGV was created to gather all scientific and technological institution that was at the moment in 1999 present in Italy. So if we go back, sorry. In Catania it was the International Institute of Volcanology. In Palermo it was something that was an Institute of Geochemistry. In Rome it was the Istituto Nazionale di Geofisica, National Institute of Geophysics, enables the Vesuvian Observatory. In Milan, the School of Earthquakes. So at the end, all of them will be shared and became just one institute. So INGV is a scientific institution, obviously devoted in the art science, and cooperates with universities and also national public institution, dealing with research in geophysics and volcanology. And you see, these are the cities. But this is only the first part of INGV, one of these phases. So the main mission of INGV is monitoring. We don't decide to do it. There is a national act that say that in Italy we have the role of monitoring geophysical phenomena in both of solid and fluid components of the Earth. So we are devoted to this. And we do this creating a seismic surveillance for the whole day, real-time volcanic monitoring, early warning, and forecast activity. What we do is creating networks of geophysical sensors and put them on the field and try to have continuous flow of observation of data. And we have three particular centers, probably one in Rome, the headquarters of earthquakes in Italy, in Naples, as you imagine, to be close to Vesuvio, and in Catania for active volcanoes. What we do, we analyze data and provide immediate communication for civil defense purposes. So we are one of the actors. We will discover the other one. INGV operates in close coordination with the Ministry of the University and the other actor, the civil protection authorities. Because we monitoring, say, there is an earthquake, as there are talks about an earthquake this morning, but they have to do something. So the other actor is the Civil Protection Department. I will talk about the Italian one, obviously. It was created after a very big earthquake in Irpinia in 1980, but it became a real department at the end of 1992. And the department, what is the role of the Civil Defense Department? Coordinate the response to natural disaster and events of C-type. We are talking about national civil protection department. So we have a different level. The A level is at local, for local events, especially municipality and in restricted areas. The B type is due to regional events, and the Civil Protection Department, from a national point of view, will be active only for national crisis, catastrophes, and so on. What about their work? They create agreement with the regional government and local authorities, and they are devoted to help to create laws that are used in prevention of risk. how can we do it, and how can we interact with the Civil Protection Department? Obviously, we don't use phone to establish connection, not only, but there is a general agreement between the two parts, the Istituto Nazionale di Geofisica e Vulcanologia and also the Civil Protection, and it is inactive, is valid for 10 years, and it is made by general agreement. We will see what happened, and this document is completed by different annexes that establish in details who does what, in particular for generic geohazard and risks. Do you have any question? So now I need your help. What do you think INGV can be able to monitor an active area, active in very large sense? Have you an idea?
Do you mean like monitors in movement? Do you mean, or
Monitor in general? We have to advise civil protection when something happens.
okay.
What can we do to do this really? I give you a suggestion. I ill, I have flu, for example. What do you decide to establish that I'm really ill? Pardon?
Install sensors?
Install sensors. For me, for example, you can measure my temperature or my blood pressure, or if I fall, I maybe need an X-ray.
Visual observations? The visual observations? So I can look at you to see if you can do it.
Yeah. So, what? Please.
Do you look to see what population is within the area and what infrastructure?
In particular, in our local situation,
In INGV, as for an active area.
try to imagine that in Italy we are more or less 60 million people, and if you exclude Sardinia, the whole Italian territory is under under seismic risk. I'm not talking about landslides, floods and so on, but due to earthquakes we have very high risk level for the whole country. As you see, I can move back if you want. Sorry, just a bit. Okay. As you say, nobody is safe. Because once we thought that in Emilia Romagna few earthquakes, it's not true. Only Sardinia is an happy location. On the other side, all the Apennines, as I told you, the part of Friuli, Venezia Giulia, very, very critical. And if you had lots of earthquakes in the area of central Italy. So,
Do you
I think-
have, sorry,
no, please.
do you have a kind of a global GPS network that you monitor
Yeah.
with motion?
Yes, I will show
Okay.
in a while. So the first thing to do is to install sensors, and we have to understand what kind of sensors are necessary or are useful to do this. So I will ask you again your help. Look at this sequence. I will not comment it for the first time. So the best thing is, the best thing is to give you an example in a real use case. So we enter in details. Please notice we are, what's this? You know, it's a seismic signal. So there is a station on Mount Etna with the initial E. We are in 2002. There is starting an eruption, so we are using a seismic signal to monitor a volcanic activity. But a volcanic activity that is characterized by earthquakes. And so using only one sensor, typically it's not true, we can monitor a change in the state of health of the volcano or in a particular area. So we have an alert, pre-alert, while the signal is growing in its amplitude, then the movement is changing. Earthquakes start, and they became more and more, they increase in number. So it was a swarm, a seismic swarm. At the end, it is very important to consider that we collect, in this case, thousands of earthquakes, for example. How many earthquakes do you imagine we have in Italy in a whole year, for example? Not of this time. Normal instrumental one. For the world territory, we register more or less 80,000 earthquakes in a year. Fortunately, most of them are only instrumental. So we have the opportunity to reveal little changes in normal activity, starting from a single element, in this case a single seismic sensor. If you multiply this activity for different numbers, I will show you now, we have built a monitoring network. So take my pressure, take my temperature, X-rays, site visit, and so on. A complete checkup of my person, and in this case, for a territory, an area, a seismic area, active seismic area, or in an active volcano area. So we started from seismic part, but we have other geohazard and risk. Lava flows. This is Mount Etna. And then we imagine another kind of risk. Do you know what's this? Ash flows. Can you evaluate how long is it? Northern part of it, Malta. This was the eruption of 2002, for example. Try to imagine what happened to evaluate the risk of this incredible output. And then the implication we will see later on civil aviation. After the Iafia local eruption, Europe will stop, and so they have to decide that it was a very important and impacting problems, because you have to decide the life of so many people, and it blocks all the civil aviation roads. Do you know why? Oh, sorry.
Well, I was going to say about what about gas and the effect on human health? Because obviously sulfur dioxide. Do you deal with those hazards as well? Because
we monitor CO2,
yeah.
SO2, sorry, CO2, and water, and HF, and so on. We have inside not only local but totally at national level geochemical department, and it is very important when we try to study the behavior of active volcano, and also in some radium, for example, for some from some cases it's very useful to study earthquakes. And that's it. I will show you only Sicily, but each of these triangles is a sensor. So we have covered a lot of territory, and we may say that Etna and Vesuvio are maybe the most monitored volcanoes in the world. It's true, because we have lots of different kind of sensors. So please help me. Do you know some of them? You know how they are, what they do?
Not infrasound.
Okay. I will tell you. Seismic.
Yeah.
What is a seismic sensor? Do you know how it works? This is a transducer between a movement, there is a mass, and it transforms in electric signals. The electric signal is an analog one. Do you know what it is? An analog signals? Yeah? But we talk with computers, so we transform the signal in bit 0101. So they use digitizer to reveal this kind of sensors. Infrasound, Marco. When a doctor visits me, want to see me, so we use video cameras. And if you want to hear me, we use microphones. But we have to hear the sound of a volcano, so we have to go down in frequency. Below 20 Hz, we don't see infrasound. But they are when a volcano breath. So we have different microphones, sorry, and at the summit part of the volcano, we have a network, and we try to register the activity of summit craters, distinguishing between sounds. They are treated as seismic signals. They are in the same condition. Often they use the same digitizer, and they are very useful because in some cases we have video cameras, but it's cloudy and we don't see the volcano, but we continue to hear. Do you know really what an accelerometer is? Radiometer is a sort of camera. GPS, everybody is wanting its own cellular phone, and we are connecting with satellites, but not the relationship is not one by one, but the GPS network is RTK, so they dialogue between them and correct the error under 2 centimeters. So we have a very precise network. Right?
Yes.
Tilt meters.
Information, reflection of the
Yeah. They are most used in volcano. Sorry. Why? Because when lava intrudes, we have a deflection of the volcano, otherwise we have an inflection. And so strain meters, magnetometers, gravimeters, video camera, fluidics, they are strange sensors because they were born to evaluate the quantity of water. They are little radars. But we try to use them to detect ash. We use common radars. FTIR is a technique of spectrum to measure the presence of gas in a volcanic plume, and the same do DOS. So I will continue. Why, in your opinion, I have written in situ? It is on field. We have only this.
You have remote sensing as well.
Remote sensing. So we use also satellites. And I have a question for you. What can you think about a drone is? Is an in situ sensor? Is a remote sensing sensors or what?
What did you say? What did you say?
What do you think a drone is? We can consider it a remote.
It depends.
Yes, it depends. So it is very useful device because you can walk and you can consider in situ like at terrain level, but you can consider also a remote sensing with 50 meters, 100 meters, 200 meters. So we have satellites, with the constellation of satellites we retrieve images, and we do some elaboration that are particular. I cited as an example what? Interferometers, interferograms. You know what they are?
Yes, sir.
Someone can explain to the others? Simon, do you want to try?
It's
Simon,
yeah.
Okay.
You take two different radar images from a date and another date. For example, 1 week in between, and you can measure the ground deformation with this, making the difference between these two radar images.
In Clermont-Ferrand, they are experts, so I know perfectly. So you will retrieve the information with the difference between two different satellite measurement, and it's like GPS. Please.
Do you use measurements about thermal activity
Yeah.
on the ground, thermal changes?
Yeah.
Thermal
We have some sensor on the field that measure temperature, but we use also thermal cameras.
Okay.
Very useful. In some cases, we are able to see lava flows that are not visible with your eyes. I will show you some picture. So,
So how many in total sensors are there? You must have.
We have, I think at the moment will be 300. Only this part. I will show in fact some numbers, but they are referred only to this part of the system.
Does the data automatically come back to your
Yes,
central?
that's the problem. That's what I have done for maybe 15 years. Because you have not only to go to the field, create the station, build it, power it, we'll see, but you have to connect with a central hub, we can say, and they have to transmit all the data continuously and what we say in real time. Otherwise, we have no information, or we have not continuous information. We have periodic one. So it's a very important work. Huge job. Days in the field. So. So, you have done your data mining exercises because we have to analyze each single sensor. Geochemical, we use a lot of multi-parametric stations. There are stations with different sensors in a unique location, using maybe the same batteries, the same solar panels, and I will tell you. So, going back a minute, the only way we know to monitor an active area is at the moment using both sensor in situ on the field and remote sensing. The more the constellation of satellite grows, the more we have images and we can analyze them. Some of them are used as raw data, where I told you about raw data this morning, that are data that coming directly from the sensor and
Raw data.
Sorry?
They are raw data.
Raw data, yes. And without any processing. Otherwise, we have in some cases a pre-analysis or a better analysis, and then we have output results. Malcolm rightly say that all of this area and all of these signals can move, and we will transmit to a central hub, and they are visualized in what we say a control room. Try to imagine that this is only a little subset of what we have. But we have seismic signals, we have video cameras, both in visible and in thermal domain. We have analysis about volcanic seismic signal. We have localization of earthquakes. Once there were 2 drum recorders that records using old pen. And it is important to monitor the monitor networks. So we have synoptic model one that say, okay, I don't receive a signal, for example, or nothing happened, I'm not sure, only it's okay. So I will show the pictures of the control room in Catania. As you read, all signals coming from remote multidisciplinary stations are transmitted to a unique data hub, monitoring center in Catania, and we have in the presence inside the control room of researcher and on-duty staff. What is the role of an on-duty staff? We have to communicate immediately significant variation of some parameters. We will see what means immediately. We will see what are these parameters and so on. And this is the relation between INGV and seal protection. We don't decide to do as we want. We have a protocol, obviously. We know who is our stakeholder on the other side, but as again I told you, we have to establish a protocol of communication between us. Otherwise, the one doesn't understand the other. It is open every day, during summer, during Christmas, during the New Year's Day, and so on. We have only the presence of 2 personnel there, for in 3 different windows time, during the morning, during the afternoon, and during the night. So it covers the whole 24 hours per day. Any questions? What is clear, nothing is clear?
How many people you are, for example, during Christmas Day? Only one or 2?
No, 2. Always 2. But they are not alone, because even if they are present in 2, we have 8 colleagues that are on duty. They are ready to yes,
work.
in case of earthquake, a seismologist can help them. In case of a volcanological crisis, a volcanologist. We have IT person also, because try to imagine that this very big framework, the station is broken, the station doesn't transmit, the station has no power, lots of problems, obviously. Are you still sleeping?
No?
So I will show you some examples of what a monitoring network is in practice. So try to imagine that we have a shelter, a little building that is able to contain what we need. And what is the first problem? Is to use, my computer is have an AC plug, that's okay. When you are in the top of the mountain, you can find the AC plug, so you have to work to provide the right energy. So solar panels, wind turbines, for example, or fuel cell. Do you know what is a fuel cell? Is a sort of battery that is I will have sorry, okay. This is methanol. This extract hydrogen, and it works with hydrogen and produce DC power, and it recharges the battery because we haven't for the whole day the sun, so solar panels are very useful, but for a part of the day, not for the whole day. In some cases we have wind turbines, but there is no wind, so we have to try to organize ourselves just to let the station continue to work. And this is a mini UMTS router that is able to transmit data as my cellular phone does. So, okay. This is a colleague of mine. This is a mobile station, because we have permanent station with their own building, but also mobile. We can use in Italy or in another country as we want. Or if we have a partnership with some other volcanoes, for example, we can move devices to monitor for a brief period the activity. What about them? Try to imagine that the height of Mount Etna, you have not read maybe, is 3,300 meters. So during winter, it's not, even if we are in Sicily, people does not care about the presence of very strong winds, snow, and so on. So this is a video camera station. You can see this is the antenna, so it is difficult to transmit data in this way. But we have also in campaign some other I will show you before, and some of mobile station that we use. We have seen some solution with power, and we try to integrate some different sensors in the same location. As I told you, that's an example. These are two digitizers for seismic sensors that are under this part, because they have to be strictly in contact with the ground, with the field. This is a GPS. These are two DC regulators for batteries. This is another kind of sensor, in general an accelerometer or an infrasound, something similar. And we have all of them in this building. I told you that we have to transmit data, so there is a problem of transmission. We have different carriers because they have to work. So one word we use a lot is redundancy. We have to guarantee that if the system A fails, the system B is active. Sometimes also the system C is necessary. So we can talk about satellite, we can talk about UMTS, radio links, Wi-Fi. What do you think about modern technology offers we try to use? And we have our Wi-Fi permanent network that is able to collect data from different parts of Sicily. And it is obviously in the same way in other parts of Italy, for example. So the part of logistic and technological aspect is very important in monitoring and especially in surveillance activities. And that is an example of the station you have. So the building is closed now, the dish of satellite transmission. Here are the solar panels, and here are the location of the sensors, some of them. Some images from video cameras that really are not cameras. They are temperature sensor for temperature, and they have different reaction when a body is hot, warm, or cold. In some cases, also when there are clouds, we are able to use thermal cameras because they are able to let us see the thermal image even if there are little clouds. This is a sequence, for example, in the real vision and what the sensor in thermal vision see. And this Southeast Korea in activity and the lava flow example. They are able to reconstruct lava flows. We use some helicopters, and maybe we can use in the future some drones to map correctly the lava flows that we are not able to see during the day, for example, because it's not always simple to detect the lava in a lava field, because there is a new lava on the old one. So you distinguish it because they have a different temperature. I was thinking about you. We made the word just to say an example of analysis of raw data. We start from seismic signals, and we use to analyze it and process it. And we try to Malcolm stops me when we have the coffee break. Oh, do you?
Coffee's at, I think about 4 o'clock. So
Oh, 4 o'clock.
4 o'clock, yeah. So probably around now, so you want to finish off.
No, this slide. Okay. So we define a method using expert systems that are software tools, only maybe both hardware and software, that are able to imitate the brain way of thinking. So we are neural networks and fuzzy logic maybe in the field man knows very, very well then, because we can imagine what a neural network is. It's a sort of representation of our network inside our brain and the synaptic connection between the neurons. And they are expert systems because they are able to learn without having seen a case for they see for the first time. We learn them to recognize something and they operate. In the same way, there is a similar action on fuzzy logic. Fuzzy is an English term, I don't know if you know its meaning. In Italian, sfumato. Yes, someone help me with the degree. We say shade, yes, but it's not. I will maybe give you an example.
Like bubbly? So let's say no clear boundaries, right?
No
So
clear
there's
boundaries.
Let's say more than one truth values. Yeah?
But it is a human behavior.
Yeah.
And that's the example. What's your name, please? Yeah.
Gregorio.
Gregorio. Gregorio, between me and you, how do you estimate the distance?
I have to answer this. I have to answer this. This
Yeah.
will be completely wrong.
About 5 meters.
Yes. You are sure that you are not 3 centimeters, and you are sure we are not. The distance between us is not 100 meters. But we don't have a measurement device, so we estimate it. A computer does not understand the estimation. It wants to know. Sorry, it wants to know exactly what is the distance between me and you. Otherwise, human beings reflect this behavior. So, Fuzzy declares some boundaries between 2 states. The same when I use some words. What is the meaning of old person or young person? It depends. I'm not feeling old, but probably I will be. And all these more than 60, between 40 and 50, more than 100. Young is 2 years, 5 years, between 2 and 10. Okay, that is fancy.
As a fish. I found the Greek word.
Thank you. That is fancy. And it really most used in microchips. Try to imagine what is an autofocus for a camera. It has to estimate the distance without using a sensor that is too expensive. But it knows that maybe it is in an interval, and it's okay, because when you focus your camera between 2 levels, that's okay. You don't make a mistake if you move your own focus to 100 meters while I'm 3 meters distant from you, okay? This discussion for what? To understand the different characteristics of a seismic signal. The seismic signal is changing, and we have different examples in various eruptions, and the system recognized that that situation is similar to one it saw before. So it gave us an alarm when some thresholds are fixed. Because try to imagine that for even if they are 2, we have about 40 monitors. What can I do when I'm here? Next Thursday I will be in the morning in the control room. So what do you suggest me to look? Earthquakes? No. Maybe the activity of Mount Etna. So we need automatic devices or tools that help us to recognize some variations. And we develop softwares, tools that are able to help us in this activity. They are not perfect, obviously. We have to validate them. We are present for this reason. And we evaluate if it is fake or something is wrong or your station is broken. But they are very useful. And we have a very important success by using these or other things. Try to imagine what happened when there is an earthquake. We have, and I stop to locate it immediately. And we have to do with the help of an automatic system.